Okay, problem number 9. It's the figure shown here shows a simply supported beam with a uniformly distributed load and a rectangular cross-section. So this is the key information. Rectangular cross-section. So the labeled points are evenly spaced along the depth of the beam. Which point has the largest absolute value of shear stress? Since this is a rectangular cross-section, this is a simple cross-section, right? So the maximum shear stress will just appear at where you have the largest Q, since T is a constant, right? And this is equals VQ over IT, right? V is constant, I is constant, T is constant. So where you have the largest Q, you have the largest shear stress. So we all know that Q max appears at the neutral axis or the centroid, right? So that is point C in the middle. Our point C here, the solution is A. And number 10. Assume the following beam cross-section experiences a vertical shear force, knowing that the factor of the shear stress is determined by tau equals VQ over IT. Right, again, this is the same equation, tau equals VQ over IT. And what is the value of thickness T for determining the largest shear stress in this entire section? Okay, in this case, again, V is a constant, I is a constant. So where you have the largest Q and smallest T, you will have the largest shear stress, right? And the Q, largest Q is here. When you cut it through the centroid, you have the largest Q. And you can find that the thickness, the smallest thickness, is actually right here. Right, you got E equals 6 mm. This is the smallest thickness in this cross section, right? So no doubt, this is where you need to determine the largest shear stress. So this E equals, the thickness equals 6. And number 11 is a concentrated load P is applied to the upper end of a 2-meter long pipe as shown here. So this end is fixed. So this is a cantilever actually. So the outside diameter is D equals 120 and the inside diameter is 104 mm. The allowable shear stress of the pipe is 75 MPa. To determine the maximum load P that can be applied to the cantilever beam. Well, again, this one can be calculated by the shear stress. Tau can be calculated by VQ over IT. Here the V, this equals P. Right, so the Q can be calculated by 1 over 12 D cube minus lowercase d cube. So that is 1 over 12 by 120 cube minus 104 cube. And you will get 50261. And the I can be calculated using these two numbers too. Right, this is pi over 64 by external diameter force minus internal diameter to the force. Right, so then you can get 4436230. So here this equation can be rewritten as 75 MPa that has been given, allowable stress, equals V by 50261 over 4436230 by T. So what is the T here? The T here actually is just D minus D. Right, it is 16 mm. Right, so here is by 16. Here in this equation you have only one variable, that is V. Right, so this V can be just solved, and it is E, right, 105.92 kilonewton. Okay, now let's look at number 12. You have a cantilever beam again. It's subjected to a concentrated load, P, that is 31 kips. The cross-section dimensions have been given. And actually, I think in your exam, the I should have also been given. Right? So if the I equals 226, this is my calculation results. I think in the exam, you should be given this number. I calculated based on these dimensions. I got 226.27. Then you just need to determine the y bar by itself, right? This y bar, in this case, is just L over 2. Right, that is 6.5 inch. Then the next step, we need to determine Q. Right, let me write it here. The Q, when you cut it from here, so we're determining the shear stress at point H. So you cut it from here, so we got 2 sub-areas. Let's see, here is sub-area 1. And here, the green color will be sub-area 2. So the Q can be calculated by adding together AD, but you have 2 sub-areas. So the first one is A1 D1 plus A2 D2. Right, so the A1 is 6.5. This is the W, right, by thickness 0.35. This is the area A1, right? By D1, so D1 will be 6.5. This is the y bar minus half of the thickness. So here you have, this is A1, this is D1. And plus the A2, D2. So the A2 here, this small area, will be 6.5 minus 0.35 minus H. This is 4. Right, so this number is right here. Is the height of this small rectangle. By the thickness is 0.285. Right, so this is your area A2. So by D2, the D2 can be calculated by 4 plus 4 is the H, right? It's from this centroid to the edge of this rectangle, that is 4. So plus half of the height of this rectangle. That is half of this, right? Plus 6.5 minus 0.35 minus 4 over 2. So you will get this Q equals 17.5 cubic inch. So here you have your D2. Then the tau can be calculated by VQ over IT. That is 31 kips by 17.5 over I is 226.27 by 0.285. This is the T, right? So you will get 8.41 KSI because you have kips here. Okay, that's A.